Hey, you're some heights, that's just because all. I have to do it. Just take from that. Yes, I think this is I don't know. It's not very dialogue. Oh, no. This is both converting to that CT. Oh, okay.
Actually got everything set up before 5:30 then, so that's pretty good.
Pretty much basically when you're like this. Well, yeah. Yeah, the issue is so this is what the actually looks like. What the heck? I can't find any documentation on it. Of like what they actually mean. That is your input. This is on your activity, your Y position. But your X position and Y position are measured off of what's in top. One is left corner, here's the left corner. Yes. But it's all positioned from the top right. Or top left. Weird. It's really weird. So it draws it out. Right. So like if you get a rectangle, it's good, but the 0, 0 is up there. So I really it being that point was actually fine. That's just still if I needed that point, and you'll use that, weird. Because it's like maybe 89. So it works underneath that rectangle. How do you even move that? Well, there's no rectangle, that's what it is. Okay, so that's the actual rectangle.
All right, so I'm going to get the lecture started. There might be more people joining us, Zoom. Well, speaking of the Zoomers. So I need to come back and let more people in because apparently a lot of people get sick. There we go. So anyway, so I got some really interesting material for today. Today's lab is brand new. Okay, this before I created this lab activity just for today, so that you guys can get some practice. Okay, because I found that in previous semesters, in exam 2, a lot of people don't know how to track down the changes of the states inside a memory-related device like that. That's all that. So we talked about it a little bit last week, and I actually wrote a spreadsheet to do circuit simulation. So simulate circuit simulation using Google Sheets. So that's kind of fun. So I was having a good time doing that. And let's see, new one. All right, so that should be it. Okay. All right, so if you're on Zoom, please type your name down, so that I know who is on Zoom, because some of these people may have used somebody else's account, so I do not recognize those names. Thank you. All right. So what will, huh?
Sharing your screen.
I am sharing already. I just need to put the I just put a window, on my other screen, so it doesn't take up space here. Yep, but thank you for the reminder. That's always a good reminder. So anyway, we are going to go back and talk about the SR latch. And this time, if you got a chance to read the announcement, I actually made a spreadsheet to do the circuit simulation, which is kind of cool. I think it's kind of cool. This is the kind of thing that I like to do. So if you go into this one here, and it has a link to a Google Sheet. This Google Sheet, does not require any authentication. You can just kind of click on it and it opens up, but it doesn't show you the code. So I'm keeping the secret sauce secret, but I give you the appearance. Okay, so this is something that we have talked about already on Tuesday. Okay, this is the SR latch in oscillation. So what I do want to talk about a little bit today is just generally speaking, what should we do, to create, to update these rows and columns. And that is going to be relevant for tonight's lab. So it's going to be quite useful if we pay attention here instead of having to watch the video, right before doing the lab. Yes.
I actually had a question that I was looking at this between classes. Looking at the off that. But so on the very first step, we start with in 0 is equal to 0, and in 1 is equal to question mark. And how did we get the value of the output? And one of the values is question mark.
We simply do not know what it is. We know there's an output. Okay.
Why would it be 1? Because we didn't really have it, but wouldn't it be like 0, 0, and the output?
Which row are we talking about?
Row.
Let me. I can zoom in a little bit. Let me zoom in a little bit here because we do have the space to zoom in. There you go. So which row again?
The one you did last.
Well.
Yeah, I'm looking for M1 out.
You mean this one?
Yeah, how can we assume that it's 1? Yeah, that's what.
Oh, there's no assumption here. Okay, so let me explain this whole thing from the beginning. So basically what we have here, so in case there are people who are colorblind, or in case the circuit requires so many nodes that it is no longer practical to color code the nodes. So I use a node ID. So everything that has the same ID belongs to the same node. So you can see how the two red ones belong to node 0. The yellow ones belong to node 1. The green ones belong to node 2. And then the blue ones belong to node 3. So this is basically a duplicate of the color coding, just in case some people are more comfortable with using the ID instead of color coding to find out which ones are of the same node. So I'm just explaining the whole thing, from the beginning. And then the columns, each column is corresponding to a port. A port basically, relates to a connection pin or connection point of a component. So a NAND2 gate has 3 points. It has 2 input ports and 1 single output port. So we talked about all of this stuff in the previous class on Tuesday already, but I just want to kind of double check and make sure. So the notation is a little bit different here. So instead of just naming the device, I also include the type of the device. So we have input pin, with the uppercase I, because it's a class name, because it describes what S is. So we have input pin Q, we have NAND2 N1, NAND2 N2, NAND2 N1, and then NAND2 N2, output pin Q, and then output pin NQ. And then for each particular object, we have the components. So if you have an input pin, the only component it has is a port. Okay, that's the only thing it has. But on the other hand, if you have a NAND 2 gate, then it has 3 different components, or if you say an array of 2 plus 1 additional one, because there are 2 inputs and then 1 output. When you're talking about an output pin, it only has 1 single port associated with it. So are we still doing okay so far up to row 3 of this table? Okay, pretty much a replication of what we talked about on Tuesday, except it's slightly different in terms of the formatting. So row 4 is basically saying everything starts with an unknown state. Okay, so when you first power up this particular device, we don't know what's going on, including the input pins. Okay, so that's why everything is an unknown, which is a question mark. Row 5 is significant because row 5, has the NC both phase, but it also has the 2 input pins both phase as well. Because this is how an external agent, something that's external to the circuit, can say, I want you to do this. Okay, so that's why we are starting. This is the beginning of the propagation. Is the input pin S starts with 0, and at the very same time, input pin Q, this is supposed to be input pin R, is also starting with a 0. So I do have a little typo here. And I'm trying to see what I can do to fix it. Okay, I know I can fix it. The actual spreadsheet we cannot see because it has the secret sauce in it, but I can still go ahead and fix it. So this way, the one that you are indeed looking at is going to be fixed too. So we'll go ahead and change this input pin Q to be corrected to input pin R. So I do apologize for naming the device a little bit incorrectly, but that should not interfere with this one. Oh, this one doesn't get refreshed. Huh, that is interesting. All right, so let me see if I can do something like this. Okay, cut all this. Change so that all goes away. Paste again. And they should all come back, but it does not correct the thing. Oh, because I fixed the wrong circuit. Never mind. Okay, that was my problem. I fixed the wrong one. There we go. All right, so let's see if it is fixed this time. So that's not expanded. Oh, right, because I need to get rid of this. There we go. Much better. But it's also not fixed here. Okay, I'll find out why it is not fixed. Because it should be, oh, okay, I see why. Another operator error, because I should be changing this one instead of the other one. So this is the name that I should change. There we go. And then over here, it doesn't, yep, there we go. So I got it changed. Anyway, so where was I? Right. So on the NC row, on row 5, okay, it is special because everything started with the changes to the input pins. So when you have a row that has input pins being changed, then you only have to propagate based on node connectivity of the input pins. In other words, this is node 0, this is also node 0, and that's why this particular cell is updated to the same value as this one here. This is node 1. This is also node 1, and this is also why column H is also updated because of this. Now, when you look at the other nodes, they should not be affected by the input node directly or the input pin directly. So none of the other ports got changed. So is that okay? All right, cool. The next row is a PD, which is basically looking at, okay, what are the devices going to do? Would any device change the output? So the way you determine what you need to update on a PD or propagation delay row is to look at all the devices. An input pin is not a device, an output pin is not a device. So in this case, we only have the NAND 2 gates being devices. So with the NAND 2 devices, you have to look at the previous rows and see if any one of the input pin is changed. And you have to test it for each device. We only got 2 devices. We have N1, which is an N2 gate. We have N2, which is also an N2 gate. So we'll go ahead and take a look at NAND 1. So NAND N1 has one of its input just changed. Okay, this is changed because it was a question mark before. It is now a 0. So as a result, I have to think about this and go like, okay, is that going to change the output of N1? The answer is yes, it is going to change the output of N1 to a 1, because this is a negated AND device, and I explained why this update should happen on Tuesday already. So I'm just focusing on the formatting today. Are we good so far? Yes, I hope so. Maybe, no. I'm not hearing any questions. All right, yes.
Negated and you probably explain this on Tuesday. If you have an input of 0 and another input of literally nothing.
Okay, what do you mean by nothing?
It's because
This one is unknown. We have the other input being unknown, but it doesn't matter because because it's a NAND 2 gate. Because if you have a NAND gate, okay, let's think about a regular AND gate first without the AND. Okay, so let's look at a regular AND gate. If at least one input is a 0, what can you confirm what the output is supposed to be for a regular AND gate? Yep, exactly. But this is a negated AND gate. So with a normal AND gate, it would output a 0, but with a negated AND gate, it outputs the negation of a 0, which is a 1. Yes.
I just want to say what my error was. I was thinking it was XOR gate.
Oh, okay. This
That's
is
what
a
it was.
yeah. It is a NAND 2 gate. It's not exclusive OR. So that's why we know this has to be a 1. And the same reasoning also applies to this one over here. So we good so far? All right. So the next row is an ANSI row, which is a node connectivity analysis node. So in this case, you only have to focus on the non-output pins. Okay. So all the pins other than the output pins, you have to look at those and you ask, well, is the node that it connects to changed from the previous PD cycle? And it only has to be the immediately above row. Okay, it doesn't have to go all the way back. So I can do this a few times. All right, so this is an input pin, and we are looking at this particular row here. So the question is, did we change this in the previous PD cycle? And then you just have to look up one row on top, and you say, nope, that did not get changed. Not a problem. Well, okay, nothing in red got changed in the previous cycle. When you move on to this one, you move up one row, and you go like, the green thing over here did change, and that's why this one is changed in the following row. Is that okay? Because PD is trying to figure out, are we changing the output of a device? NC, on the other hand, is asking, if we did change the output of a device from the previous PD, where does that thing connect to? I need to update everything that it connects to. Is that okay so far? All right. So that's why, all the green ones, including this one and this one here, they were updated because of this one here. All the blue ones, including this one and this one, were updated because of this one over here. Yep.
They always match the same number of, right?
They always match.
The same number of rows. So you said the green one was on top,
Mhm.
as a 1, and so automatically the green rows below are all going to be 1s.
Yes. Yep. And everything that is not changed will remain as blank. Okay. So after this, we do another PD. We have to do another PD because this particular NC updated some of the inputs. Which input did we update? This one got updated because it used to be unknown. It is now a 1, so it's a change. This one too, it used to be an unknown, it is now a one, it is also changed. So that means I need to recompute the output of N1, and I also have to recompute the output of N2. Well, what do you think? What do you think should go here? Why is it blank? So, sorry?
You want us to figure it out?
No, this is the correct answer already. It is blank because it's not changed. We only write a number, we only write something in the cell if it is changed from before. The output of N1 is not changed, even though one of the inputs of N1 got changed. The output of N1 remains exactly the same because input 0 of N1 is still a 0. So that means, the output of N1 is still a 1, which means it is not changed from row 6. And if it's not changed, I do not put a number there. I just put a blank there so that I remember, okay, it's not updated. Is that okay? Now, why do I use this notation? Because this way I can easily tell whether I have a steady state. In this case, if you look at the entire row 8, okay, if we look at the entire row 8, you can see that nothing got changed. Okay, after one propagational delay, nothing is changed. So that means I don't need to do another node connectivity analysis because nothing got changed after the propagational delay. So this means the device, in this case, the SR latch, is now at a steady state. It will stay indefinitely like this unless I change one of the input pins. Are we good so far? Yes.
Real quick question, if we started at 1, 1, instead of switching from 0, 0 to 1, 1, would we call that an unsteady state? We're not able to.
It would still,
for it.
well, it would still be a steady state, except you just don't know the output of a lot of things. Because 1, 1 is going to preserve what they used to be. But since we don't know what they used to be, we just know that they are still the same as what they used to be, so we still don't know what they are. So it is still a steady state, it's just a unknown steady state. We know it is steady,
But it could be unsteady,
huh?
but it could be unsteady, right?
No, it cannot be unsteady.
It can't be unsteady.
If you start with 1, 1, it cannot be unsteady. Unless you know that it was 0, 0 before.
But I'm saying it could have been 0, 0 before, right?
It could have, that is true. But we cannot know whether it's steady or not in that case. So that means it makes it very impossible. It makes it very difficult without the analyze. But in this case, it's not an issue because putting the two input pins to 0, 0 always end up with a steady state. All right. Are there any questions up to row 8? So row 8 is the steady state, and it is the result of using 0 and 0 for the two input pins S and R. All right. So once again, this is the material that we have already started to get into on Tuesday, and today we are just kind of going over this a little bit more, but we are focusing on the format this time. Row 9 is a little bit special because even though it is just an NC state and node connectivity row, we can also see that both inputs got changed this time from 0, 0 to 1, 1. And that's why they're both phased. Okay, so all the changes to the input pins are both phased because they are coming from outside of the device. They're not changes because of the device or because of the connectivity. So that means we have to use the node connectivity to update everything that is red. This is red. So we have to update the other red cell on the same row. This is yellow. We have to update the other cell that is also yellow on the same row, like that. Is that okay? So it is a little bit special compared to the other node connectivity rows because we are spreading within the row instead of spreading from the row before this particular row. So then what do we get? The next one is PD. So once again, when you're trying to figure out the values of the cells of a PD row, what you need to do is to think about the devices. And you ask, is there a device where the previous row changes one of its input pins? Okay, so you have to identify what devices we are talking about. We have N1 as a device, we have N2 as a device. So with N1 as a device, these two columns are representing their inputs. So we can clearly see that this one got changed. So when this is changed, then we have to look at the output of the same device and ask, after a propagational delay, is the output of N1 going to change? And the answer is yes in this case, because we can see that in 0 is 1. This is from the row right before. And then in 1, the last update was actually 2 cycles ago, but it was also a 1. So that's how we can tell that in 0 of N1 is a 1. In 1 of N1 is also a 1 at this point. So because you have 1, 1 as the input of a NAND gate, the output will now be updated from a 1 to a 0. So that's why we have to write down the 0 here, because it really is changed. So are we good with that analysis? Okay. So with the other one, it's kind of the same deal. With N2, we also have to analyze the inputs of N2 and see if any one of the inputs got changed from the previous NC cycle. And we see this one is changed. So that means we have to recompute the output of N2. So that has to go here. This is a 1, but this one is a 1 too. It's just that that 1 was established earlier. So we have 1, 1 as the input of N2, which means the output of N2 needs to be a 0 at this point. But that 0 is different from what it used to be. And that's why we have to write the 0 here, because it is an update from before. So we doing okay with row 10 at this point. Yep.
Just a little thing, do you by chance happen to put down like a border around the 2 different gates? Like,
Oh, yeah, we can do that. Sure.
because now we have a clear look at how it.
Sure. So let's do it that way. And then, nope. And then we have to look at borders. I need to, oh, they don't have anything
The
specific.
The
Huh?
upper right one, just use the,
This one?
yeah.
Yeah, I guess so. That'll do it. I was trying to, kind of cap it here, but there's no need to cap it. So these 3 also belong together. Like so. Yep.
In order for the input pins to be 1 for both, does that have to first stabilize? Or can you just?
We note it is at a steady state already, so that's why we can change the input pins. So normally you want to wait until it reaches a steady state before you change the input pins.
So you can't start at 1, 1.
You can
You can't skip like steps 1 through 8.
these 2 can be 1 1s, but as you talked about, how if you transition from 0 0 to 1 1, it will go into the oscillation. So that's why we don't want to start with 1 1, because there's a potential that when you first started the machine, it was 0 0 to begin with. Yes.
How would we word NC if you're just saying we're updating the nodes?
So NC, which row are we talking about? Because there are 2 different NC rows. We have the ones that are both faced and the ones that are not both faced.
Second.
Okay, so with this one, we are basically asking, did any PD update from the previous row update, other pins, other ports as a result? So because on row 10, we have, the output of N1 changing. So everything that it connects to would also have to change. So that's why in 0 of N2, as well as the port of output pin Q also got changed to 0. So let me highlight the cause and effect. This change is leading to these 2 additional changes. And then this change is leading to these additional changes. Yes.
That kind of like the wire, how it goes out.
Yep. NC has to do with the wiring. So basically, typically, not always, but typically when you look at a node, only one connection goes to an output pin, and then the other pins or the other ports connected to the node are typically input pins. So you only have one port that can potentially update, but then the other ones have to follow. So NC is basically just asking if the output port of a particular node is changed, what other ports is it affecting, because they're all from the same node. Okay, so we okay with this format? It is also explained in the lab instruction, but I just want to make sure that I have a chance to talk about it in class, so this way I can answer the questions more interactively. And I'm looking at the chat channel, and there's one question of what is NC and PD? My answer is, you might want to watch the video recording from Tuesday. I know how annoying it is, and that's kind of the point. All right, so you can also see, at some point, we can definitely see that it is a repeating pattern, which means, this oscillation is not going to stop. It will never reach a steady state at this level. Is that okay? Right?
The oscillation in the program, how do you get rid of that or just slow the program?
You can always change the input pins. As soon as you change one of the input pins, so it's not 1-1, it will stop the oscillation. So the oscillation only continues because both input pins continue to be 1-1. So the external agent, the thing that is external to the circuit, can change one of the input pins. Either one is fine. If you change either one to a 0, then the oscillation will stop. All right. So do we have any additional questions about this diagram or this spreadsheet? Go ahead.
This is what our lab's based on.
Your lab is based on this, but it does not have the oscillation. So it has some other changes to the 2 input pins leading to steady states. So from that perspective, it's actually quote unquote easier to analyze. And it also has shorter questions, and you can always resubmit as many times as you want. So this way you can kind of cross-check to make sure that you're on the right path before you go too far into it.
Yep. Will the lab always start with 0, 0, or will it start with like 1, 0, 1, 0?
I think 0, 0 is a safe way to start a SR latch, because you know what it's going to do. You can start with 1, 0, 2, that's also steady. 0, 1 is also steady, or from whatever initial state you're going to 0, 1, it's going to be steady. From whatever initial state it goes to 1, 0, and the other one is also steady. The only thing that is not stable, the only thing that leads to oscillation is from 0, 0 to 1, 1. That transition is the only one that leads to oscillation. All right. So are there any other questions about the SR latch or how to make this table? All right. If there are no questions, then we are going to move on and we'll go ahead and talk about let me see. This one is from the announcement, so you all have access to the spreadsheet that I showed earlier. So what we'll do next is we are going to move on and talk about other memory devices. Because the SR latch is the first one, it is the most basic one. And if we do a quick analysis of the SR latch, we will find that it has a very interesting table. This is the truth table of an SR latch. If both inputs are 0 and 0, the outputs are guaranteed to be 1 and 1. Okay, we observed that on Tuesday already. If S is 0, R is 1, then the output is also very deterministic. Q becomes 1, and Q becomes 0. It is deterministic. if the S pin is a 1, the R pin is a 0, the output will still be deterministic, except in this case, Q becomes a 0 and NQ becomes a 1. So the first 3 rows are pretty standard, and we can kind of understand, you know, what's going on with the first 3. The last one is a little bit funky. If the inputs of S and R are both 1s, then the Q and NQ are marked with NC. Now this time NC does not mean no connectivity, it means no change. It is basically preserved, and it will just be preserved from what it used to be. So to illustrate this, the best way to do it is to use Logisim. So let me go ahead and start up Logisim and give you a quick demonstration. So let me see how quickly I can start up Logisim. There we go. So here's Logisim, and we already have worked on the circuit like this, so I got it already done. And this one is causing the oscillation, and that's why I wired it a little bit strangely. So instead of doing it that way, I'm going to wire it up the same way as before. And I'm going to restart the whole thing. Okay, so let me go ahead and now that won't help actually. Never mind. All right, so we want to do 2 things. Okay, it's 0, 0 right now, and I'm going to change 1 pin at a time. We'll change the S pin from a 0 to a 1, and you can see how the output becomes Q becomes a 0 and Q becomes a 1. And if I change R also from a 0 to a 1, you can see none of the output is changed. Are we good so far? All right. So what I'll do is I'm going to take a snapshot of this. Okay, so I'm going to take a snapshot of this so I can easily remember this particular stage. And then I would use a program to show that. There we go. And we'll make this one stay on top too. So this way we can keep an eye on what it used to be, like this. And then what we'll do is we'll reset both input pins back to 0, 0. Okay. So we know when both input pins are 0, 0, both outputs will be 1 and 1. Okay, we know that already. But this time, instead of switching the S pin from a 0 to a 1 first, we'll switch the R pin from a 0 to a 1 first. And you can see that the outcome is a little bit different. This time, the Q becomes a 1, the NQ becomes a 0. And then now here comes the magical step. We're going to change the S pin to also go back to a 1. And then you look at these 2 diagrams, you go like, whoa, that is a little strange, because both inputs are 1, 1s in both cases. But because the path leading to both inputs being 1, 1s were different, the outputs are different. You all see how transitioning from the input 0, 1 to input 1, 1 versus transitioning from the input of 1, 0 to 1, 1 leads to different states for the outputs. Is that okay? And this is why it is the most basic memory device. It remembers. So when both inputs are 1, 1s, it is basically just saying, okay, this is the thing, okay, this is latched now. The state is now latched until we change it later on. Is it a really primitive memory device? The answer is yes, okay? Because the way you change the state is to use the S pin and the R pin. S stands for set, R stands for reset. So when the set pin goes from 1 to a 0, we are actually setting the Q pin to a 1 and then resetting the NQ pin to a 0. When we change the R pin to a 0, we are resetting the Q pin to a 0, and then we are setting the NQ pin to a 1. So that's why it is called as an SR latch. We have 1 wire. Okay, you can think of this as a physical device where you have 2 levers. Okay, 1 lever is going to set it, 1 lever is going to reset the state of the thing. And when both levers are released, it just maintains whatever state it is currently in. that okay? Is that picture doing okay in your mind, or is it making it worse? No, yes, no. I'm trying to think of an analog device that can do the same thing. Yep.
They do it on the website,
Huh?
they show it using the logos.
Yes, I can do it. Okay, so let's go ahead and reset both pins back to zeros. Okay, 0 and 0. Okay, and we want it to be we want Q to be a 0. So this means, you know, I want to leave the R pin to be a 0. And then I can leave, you know, I can bring both pins back up to 1s. So now we are getting to the reset state. Is that okay? On the other hand, if I want Q to be a 1 and I want to remember that state, then I change the S pin from a 1 to a 0, and then change it back to a 1, and now it has remembered the state of, you know, the Q pin being a 1 and the NQ being a 0. Is that okay?
Does anyone use them?
Yes, not by itself, because by itself is really primitive, but we build other circuits on top of this so that it becomes more usable.
So the circuit is symmetrical, right? So the S
Yep.
and R, you could just flip them and
Yes.
flip the Q and Q.
Yep.
So it's Q and not Q, right?
Yes, NQ is just not Q.
So what we're really looking for is like the Q, that's what matters to us. So that's why.
Sometimes the NQ matters too. Sometimes the NQ also matters, but in some circuits, you know, the NQ does not even have an output pin, which because most people do not care about the NQ. But there are certain circuits where it does matter.
Because it's set Q, reset Q.
Yeah, but remember, there's one state where both pins are 1s, because when both input pins are 0s, then both output pins are 1s. So NQ is not always the negation of Q. It's just that in most cases it is. So sometimes it is still useful to expose NQ as a pin, although in many cases it is not the case. In many cases, we really only need Q, which is reflecting the state of the SR latch as a whole. Are we doing okay so far with this circuit? But don't you think this is a really smart circuit using only 2 NAND 2 gates, and then we have the most basic ability to remember something. Now, the way you use this is really kind of awkward, but it does work. All right. So what we'll do next is we're going to build a next level of device using an SR latch this time. So let me go to the notes. And let's see. There we go. So what we'll do next is we're going to do a D flip-flop. Okay, this is what we call a level sensitive D flip-flop. So I know, you guys do not like to read it like this, because it's all text restriction. But we can see one thing for sure is we are going to use an SR latch that we built earlier as one of its components. So that's what we'll also do in LogicSim. It will basically build what we call a level sensitive D flip-flop. So let's go ahead and build that circuit in LogicSim. So let me switch back to LogicSim. And this time I'm going to rename the main circuit to SR latch, because I just built myself, a SR latch. And I'll just call it an SR latch. And I'll take a look at the appearance. And I'll give these pins names, even though I already know which one is which one, but it doesn't hurt to kind of give these guys names. So this way it becomes, it becomes impossible to misuse the pins. So we just have to move them around a little bit so it looks nicer, like so. And that over there. Okay. So now we're going to build another circuit. So we go to project and then we just say add circuit. This time we'll do a level sensitive D flip-flop. There we go. All right, so now we have to, get some input pins. So this one needs, if I remember correctly, 2 input pins. One input pin is called the D input pin, which is data. The other one is called EN, which is enable. Okay, there we go. It also has one single output pin, which is just Q, which is the state of the D flip-flop. So we'll call this one Q. And then I cannot remember the circuit. I go back here and take a look. It has 2 output pins, NQ is also here. So we'll also make NQ as an output pin. Like so, and I don't need this diagram anymore, so I'm going to close this one. All right, so now we just need to figure out what else do we need. We need 2 NAND gates, just like the other one. So we're going to have to use 2 NAND gates, and the lazy way to do this is to basically quote unquote borrow or teleport these 2 NAND gates out of the SR latch. So we'll go ahead and shift click these 2, do a Control C to copy, go to the new circuit, and then do a Control V to paste it here. And they still preserve the name of N1 and N2, which is great. That's what we want. We also need a NOT gate. Okay, so N is really just a normal, regular, boring negation gate. So it's just a NOT gate here. It has a name of N. All right, so now we need to hook these things up. So we want to find out, how these nodes are going to be connected. So we have the D data pin, the input pin D, connected to the first input of N1, and then it's also connected to the negation gate N. All right, so let's go ahead and do just that. So we're gonna be doing okay, I'm switching between the 2 just so that I can see the connectivity. All right, so that's one node. Okay, this is one single node. It is connecting a input pin to 2 inputs of the devices. Okay, or 2 input ports of the devices. The next one connects the EN to the second input of N1 and the first input of N2. Okay, that's not too hard. So we'll go ahead and align things a little bit so it looks nicer. So we'll go ahead and hook it up like this. So that's our second node. Our third node connects N.out to N2.in1. Oh, okay, I made a mistake earlier because this is not, okay, never mind. I made a mistake here. Okay. Oh, okay, well, that's okay. I can still fix the problem by moving this up. There we go. Okay, so that's fixed. So the third node connects N.out to N2.in1. So it hooks up from here and then all the way down here. The fourth node goes from N1.out to SR.s. Okay, so I haven't placed that component here yet. So we go to SR latch. So the sub-circuit that we have created can be used as a component, just like the rest of the components. We learned this from the 3x3 carry look ahead adder. So we just pick up one of the SR latches, slap it here, and then we go like, N1.out go to SR.s. So this one goes to this one here. And then the next one connects N2.out to SR.r. So we connect from N2 to N2 out to SR.r, like so. And then the Q goes to Q, NQ goes to NQ. That part is also kind of boring, nothing really exciting here. Because all we are trying to do is to bring the state of the SR latch to the outside world. So there's really nothing too exciting going on here. And of course, the first thing you guys notice is like, Jack, you messed up somewhere because the output pins reports error. Well, that's exactly what is going on when you start an SR latch with both inputs being ones. So that might answer your question earlier. Because it's a no to begin with, and then you just say, SR latch, your both inputs F and R are both ones. So the SR latch is just going to go like, okay, fine, I'm going to preserve my current state, except we don't know what it is. So that's why both outputs are put E, which stands for, we don't know what it is. That's basically what it is. So how do we use a device like this? So E is an enable, which means when EN is a zero, it is disabled. The device is permanently disabled. So that means you can change the D pin any way you want and nothing happens. But the moment you change EN from a 0 to a 1, then D is going to be mirrored to Q. NQ is really just the opposite of Q, so we are not going to pay too much attention to NQ. So at this point, it is called level sensitive, because when EN, as long as EN is a 1, whatever state D is going to be remembered and mirrored to Q as an output pin. Is that okay? So we can flip the pin a few times so that you can actually visualize that. So now we can go to the D pin and say, yes, let's go ahead and change it. Look at that. Yep.
So the EN's like an on switch. And D.
It's called enable. It's not so much an on switch. It is basically it's determining whether the device should pay attention to the D pin or not. So when EN is a 0, we are basically telling the D flip-flop and say, don't mind what the D pin is, just maintain your current state. When EN is a 1, we're telling the device and say, hey, pay attention to the D pin. Whatever D pin is, we want to duplicate that state to the Q pin. Yep.
So if we turn EN off and we change D, nothing will change.
That is correct. So we'll go ahead and give it a try. Like, turn this off, flip this one, nothing happens. So this is called a level sensitive D flip-flop. So the analysis of all the things that we have done so far can also be done using the same table that we have talked about earlier, except this time it gets a little bit more complicated because we also got a little bit more components, but it doesn't change the way we approach the problem. Yep.
Since they mean the state with the star latch.
Yes, the SR latch is the actual only device that can remember anything. The 2 NAND gates are only here to make it easier to use it. Look at the 2 NAND gates as a user interface. That's basically all they are. It's instead of having a set and a reset, which is kind of hard to use, now we have, this is the state that I want you to copy, but don't do anything until I say okay. So we good so far with a D flip-flop. So D flip-flop is now starting to resemble, what we like to use inside the processor. But it doesn't have any timing control. In other words, as long as EN is a 1, it will keep updating itself. Whatever D pin is experiencing, the Q pin will mirror. Sometimes we need timing control. In other words, I don't want you to update all the time. I only want you to update right at this moment. So that would be the next device that we are going to talk about, which is an edge sensitive D flip-flop. Okay, this is a level sensitive. The next one is called edge sensitive. So if I go back to the notes, because I do want to make sure that we know where to find the description, D flip-flop without any name is level sensitive D flip-flop. The next one up is edge sensitive D flip-flop. And this is the design of the D edge sensitive D flip-flop. And you can see this one is a little bit more complex. It uses 2 SR latches. The first SR latch is called S. The second SR latch is called C. It has a 3-input NAND gate and then a 2-input NAND gate, 2 input pins, clock and data, and a single output pin of Q. So we are going to go ahead and take a look at this one. Okay, we'll build a circuit in LogicSim and see how it works. So let's go ahead and go back to LogicSim. And this time we'll go to project, add another circuit. And this time we have ESDFF or edge sensitive D flip-flop. And then we'll go gather the components first. We have two input pins. One is data, which is also just D. The other one is the clock. And then we have one single output pin Q. We need two SR latches this time. So we go to SR latch, and then we basically slap two of those in here. And we have to start to name these things. So this is data, D. This one is clock. I just call it CLK. This is SR latch S. Oh, nope, that doesn't do it. The label is up on top. So this is S. This one is C. And then we have a single output pin of Q, like so. All right, so now we need the NAND gates. Okay, so we need a pretty typical two input NAND gate. So I'm going to borrow the NAND gate from the other designs again. So click, Control C, go back to this diagram, Control V, and we need to change one of them to a 3 input. So I need to look up which one we're supposed to change. So N1 is the 3 input NAND gate. So we'll change this one to have 3 inputs, which basically means the output is the negation of the first input and the second input and the third input. So it's basically doing a 3 parameter AND and then negate the output. Okay. All right, so now we're going to do the most complicated part, which is you're figuring out the connectivity and whatnot. So this time I'm going to change my ordering. I'll start with the end because I know C.out. Oh, where's the name C? That's not where I want it to be. This is where I want to put it. All right, so we know C.Q is basically just mapping to the output pin Q. So that's what we'll make the connection first. And then we'll also go backward and see who is changing the C.S of C.S. So C.S connects to S.NQ. It also connects to N1.in0. All right, so this circuit can get a little bit hairy to look at. Let me try to figure out where D is connecting to first, because D only connects to one pin. It connects to N2.in1. Okay, so we'll go ahead and flip the order a little bit here. And this one goes here. And then we want to look at the clock pin. It goes to S.R as well as N1.in1. So this clock pin here goes to the middle pin of N1, because that's in 1. But it also goes to S.R. So this is S.R here. Not sure whether I want to kind of do it this way. Yeah. I mean, what is the worst that can happen? I just end up with an ugly circuit. It will still be functional. All right, the third node connects N2.out to N1.in2. Okay, so we take this one and then we connect it all the way back to the third input of N1. It also connects the same thing to S.S. So S.S is right here. Oh, okay, that's not too bad. I mean, it's kind of on the way. Now we work out this particular node. N1.out goes to N2.in0. So this one goes, okay, that's not too bad. Could have been a lot worse. And then it also goes to C.R. Okay, so this is C. C.R is right here. Okay, that's actually kind of nice. I'm not complaining. Okay, S.NQ goes to N1.in0, then goes to C.S. So we're looking at S.NQ to the first input of N1. So we're looking at this one here, going to this pin over here, but it also goes to this pin over here. Let me just double check and make sure that's the case. Yep, it is. All right, so that's not too bad. We have a little bit of crossover, but it's not too bad. So, and I think that's it. Okay, so we do have, okay, so how do we double check and make sure, how do we do a sanity check of this circuit? We want to make sure that none of the input pins are not connected. It's okay to leave an output pin or an output port not going anywhere, but it is not so okay to leave an input port not connected. So we look at all the inputs, N1 has 3 inputs, they're all connected. N2 has 2 inputs, they're all connected. The SR latch has 2 inputs, they're both connected. The CSR latch also has 2 inputs, they're both connected. So I think from the sanity check perspective, the circuit is okay. So now we just want to say, but what does it do? What do you mean by edge sensitive? So right now, just like the other circuit, if I flip the D pin or the data pin, nothing is going to happen much, okay? At least not to the output, okay? So you can see, how it is not changing the output Q pin. So that means, okay, so it's useless. So let's just say that we want to remember a state of 1, okay? So the data pin has a 1, and this is what we want to remember. Before, we have a level sensitive nature. The enable is level sensitive. This time it is edge sensitive. What does it mean by edge sensitive? Edge sensitive means the Q pin output is going to update to the same state as the D input pin only at the very instant when CLK, the clock pin, goes from 0 to 1. When the clock pin goes from 0 to 1, it is called a rising edge because it is, if you draw the edge, it looks like this. It is called a rising edge. So this particular circuit is sensitive to only rising edges of the clock pin. Only at that instant of time when the edge happens, when the transition happens, it will mirror the state of the D input pin to the output Q pin. All right, so we want to take a look at it, right? We want to kind of trigger this to happen. So let me go to here and just turn it from a 0 to a 1, and we can see how the Q pin is now updated. Now, you guys might be saying, well, maybe you just have another level sensitive D flip-flop, right? How do we test? How do we make sure that this is just not another level sensitive D flip-flop? How can I test? Change the D right now, right? Because with the other design, as long as the EM pin is a 1, if I change the D, the Q is going to change too. If this circuit performs the way I described it, the edge is now stable, right? We don't have an edge anymore. The edge has already happened. So that means if I continue to change the D pin, it should not affect the Q pin anymore. Does that make sense? Okay. Right, so let's go ahead and do that. Okay, so I'm going to go back to the D pin and change it, and you can see, oh, nothing happens to the Q pin. Maybe it is also sensitive to a falling edge. Nope, not sensitive to a falling edge. But if I make the clock pin from 0 to 1 again, I will once again have a rising edge, which according to what I told you, it should update the Q pin to a 0 this time. Does that make sense? Okay, so let's see whether that is the case or not. Blink. Yep.
And that happens whether or not D is on or off.
Say that one more time.
So can you turn it off while D is on?
Okay, so what do you mean? What do you want me to do?
So turn Q on.
Turn Q on.
So the Q on the
Oh, Q. Okay,
Yeah.
Q. I cannot control Q directly. Q is only responding to the entire circuit. I can only change the input pins. How do you want me to change the input pins?
block.
Okay, change it to a 0.
Yes.
Okay, and okay. So if I change the clock pin back from 0 to a 1, what do you think should happen? Q should change to 1. Okay, that is exactly what it does. So this is an edge sensitive D flip-flop. So why do we need something to be edge sensitive? It controls timing. Okay, so it controls timing, which means this D pin here most likely is coming from something else. I don't want the D flip-flop to update all the time because I only want it to update when the data presented on the D pin is valid. So why do we have to wait? Well, maybe we have an adder right before this, okay? Maybe this is remembering one of the bits of the sum of an adder. So we kind of have to make sure the adder is done before we update, the output here. Okay, so that's basically, this controls the timing. I'm trying to think of an analogy of, what these things are really doing, why we have level sensitive versus why we have edge sensitive. So if I imagine this is an orchestra, I know very little about music, okay? But imagining this is an orchestra because I can kind of imitate what people do senselessly. So you guys are all, we have a violin section here, then we have a trombone section over there, then we have a cello section over here, and so on. I'm the conductor, okay? So when I wave my baton, that is timing. Okay, you guys all have to watch me and go like, okay, make it faster, faster, faster. Okay, but sometimes I would look at very specific people and go like, that means I want you to kind of don't play so hard, okay? Play a little bit softer. So the EN allows me to direct my attention to individual people or sections in the orchestra. The clock pin, the edge sensitive nature, allows me to synchronize the instruments. So one is about synchronization between the instruments. The other one allows me to specify, a particular section and go like, okay, I want you guys to pay attention to this particular thing. So that's kind of what is going on between those two. So the thing is, a lot of times we need both. We need to control who is paying attention and when that thing is going to update. So that means very often we need edge and level sensitive D flip-flops, which is what we're going to do next. Okay, so we are basically building circuits that are increasingly complex, but they can also handle more different types of situations. So if I switch back to the notes here, and we'll go all the way down to section 6. Now we have a clocked and gated D flip-flop. Clocked is the same thing as edge sensitive, and gated is the same thing as a level sensitive. So those words basically mean the same thing. So in this case, I gave up on the text description. I just kind of used the pictorial representation here. So this one, if I were to emulate it, there's really nothing exciting going on because we already know what level sensitive means. Okay, if the level is 0, if the gate is 0, nothing is going to happen. We also know what the clock is going to do. The clock means, if we have a 0 to 1 or rising edge condition, then we pay attention. Only at that moment we pay attention to the input, which is the data pin. So in this case, we have two conditions to satisfy in order to mirror the data pin to the Q pin. First, you need to make sure the EN is a 1. In other words, the conductor is saying, I'm talking to you, but don't play that note just yet, okay? I just need you to pay attention to me. But once EN is a 1, and the clock pin transitions from 0 to 1, that is when the data pin is mirrored over at the Q pin. So it combines the two properties of the two D flip-flops that we have talked about. Is that okay? All right. So you might think this has to be the end of it, right? We have now combined. We started off with the SR latch, which is a memory device that is really primitive and difficult to use. Then we transitioned to a level sensitive or gated D flip-flop, which is a little bit easier to use because I have one pin to specify what the device is supposed to remember, and another pin to say, are you supposed to mirror? Okay, so we have two pins to control the gated or level sensitive D flip-flop. And then we talked about the edge sensitive D flip-flop or clock D flip-flop, where you don't really say when, you don't say whether, but you say when. Okay, it's only when we have a rising edge of the clock that it will pay attention and mirror the input to the output. This one is a combination. If you want any updates to happen, you have to make sure EN is a 1 and the clock is also seeing a rising edge, and only at that moment, the input, the data input will be mirrored to the output Q. Are we doing okay so far? So you might say, that has to be the end of this whole thing, right? I mean, how can we make this even more complicated? So the answer is yes, we can make this more complicated, and it is necessary to make it more complicated. So the next one looks like this, okay? So when you look at this one, you ask, so what has changed this time? What is the one extra in this particular design that was not in any one of the earlier designs? The reset pin, okay? So the reset pin turns out to be very important in a computer because with the reset pin, you can tie this reset pin to a reset circuit on a computer, your cell phone, your Fitbit, and so on, so that when the device powers up, everything starts up at a known state. Okay, so the reset pin goes to two gates here. One is an OR gate, one is an AND gate, and their presence here is to make sure that when the reset pin is a 1, we change the FRC latch to a known state. That's the job of the reset pin. So in a real computer, you have a device called a watchdog device. A watchdog device is kind of a funny thing. It is called a watchdog because if it's not hit periodically, then it will reset your computer. So when your computer is healthy, when your operating system is working the way it's supposed to, then every so often it's gonna send a pulse to the watchdog to reset the timer. But if your operating system has hung up, okay, one of your driver has misbehaved, then your operating system is locked up, then it won't quote unquote hit the watchdog anymore. So the watchdog has a timer. When that timer expires, then it will assert a system-wide reset pin. Okay, and that system-wide reset pin will reset the processor, it will reset all your peripheral, it will reset the chipset, and so on and so forth. So that this way your computer can get back into a quote unquote known state. Sometimes that reset pin also connects to what we call the NMI, which is the non-maskable interrupt. And this is how you get into the blue screen of death in Windows. Is the watchdog not getting hit periodically? Something has gone wrong, like really, really wrong. And then the watchdog circuit asserts the NMI pin of the processor. The processor gets a non-maskable interrupt, which means it will happen. And that particular handler is what is responsible to give you the blue screen of death. Typically, all we can do is to dump all the memory content onto the hard drive for diagnosis purposes later on. All right, so we're gonna take row today, okay, because it is kind of important to do that. So let's see, row taking today is the 9th, and I got this one all set up too, so it didn't take much time. So this is the QR code. You guys can do the QR code, but I have not released it yet. So give me a second to release it. Okay, save and NC is the word, by the way. NC, node connectivity is the word. So right here, the access code is NC. We are just in time for rotating. Yes. No, I did not. Okay, that's good. So basically, what I have done is changing the layout of the time for the lectures. I compressed the discussion of all the different memory devices to a shorter amount of time. So this will give me a little bit more time later on to talk about what you guys will be very excited about, the actual programming part of this class. But this class is no longer called Assembly Language Programming for Microcomputers for many reasons. The first one is what is a microcomputer? It's a really archaic term for a PC. Your parents may know that term. Your grandparent may know that term. Because before microcomputers, guess what we had? Mini computers. So we had mini computers, microcomputers. So the computers that we have now, which is disguising as a phone, should be called nano computers, right? And then your Fitbit should be called pico computers, and so on, right? And then later on we'll have what, femto computers. All right. Your lab is all prepared, so I want to give you the information before I kind of go back to basically a roadmap of what we'll be doing after the break. So let me go back up and go to the lab so that you have the access code to the lab. All right, scroll. All right, so these two are corresponding to your lab today. And this is NC and PD, once again, is not North Carolina Police Department. In case somebody is wondering. Let's see, the code is a little bit harder to get to with the new redesigned thing, and I might need to kind of zoom out again, go to build, because this is how I can get back to the access code. So the access code is part of the settings. Students have already attempted this assessment. How is that possible? Okay, so the access code is step master. Because when we are going through the NC and the PD cycles, it's taking one step at a time. And I'm pretty sure step master is trademarked. As an exercise, we push it. All right, so, but I do want to use this opportunity, and I need to release that too. I just released it, so that's okay. Okay, that was one thing that I wanted to do. Right. So when we come back from the break, okay, the spring break, we are going to, okay, I want to show you what we're going to do after the spring break. So where we are at right now is to talk about D flip-flop and other basic memory devices. And then the next two labs-ish is going to talk about other components of the processor. So we are basically building up the components that will go inside the processor. And then at that point, once the processor is built, you guys are not going to build the processor. I have it pre-built already. But once we have the processor built, then we'll actually start to write code. But before that, we have to understand, how instructions execute. In other words, we have the 4 cycles of instruction execution to talk about. It is the instruction fetch cycle, decode, execute, and store. Now, in most other classes, I can only talk about those 4 cycles in a very abstract way, because you can't really look inside the processor and say, oh, it's doing a fetch right now. Look, it's doing a decode right now. But with this class, because I made my own processor in LogicSim, I can actually do that. I can do clock by clock and say, right now, it is doing a fetch. Look at the pathway. It's going from memory into this register. It is a fetch cycle. And then I can also show you exactly the moment when it decodes the opcode, because that's when the output of the register goes into another register with some modification. That's the exact moment when decode happens. And then I can also show you the execution, because we can see how the microcode is organizing all the other components inside the processor to do what it is supposed to do what the instruction is supposed to do. We can also see the store cycle, because we can also see how the registers connect to the memory and say, hey, we want the content of this register to update that location over there. We can actually see everything with the toy processor that I have designed. So that's why, in this class, we are not using an Intel processor. We're not using the ARM processor, which is fairly common these days with classes like this. We're using the TTP, tax point processor. It's a very simple processor, so simple that it would fit in Logic Sim. But the idea is we can visualize, we can actually identify exactly when what happens. And as a result, assembly language programming is no longer about, oh, the syntax, okay? This syntax doesn't interact and blah, blah, blah. The syntax is really just declaration. Okay, the syntax does not determine what the processor can and cannot do. The processor's own design, the organization inside the processor determines what it can and cannot do. And in many other classes, people get it all reversed. They look at the syntax and go like, so if I want the processor to do this, I just have to put parentheses around this thing. No, it doesn't work that way. Okay, the parentheses are nothing more than just dressing up the instructions, so it's easier for us to understand. The limitation is always the organization inside the processor. So hopefully the way I organize this class makes it easier for you guys to make an association of how does this happen? How are we adding these two numbers and storing the sum back over there? How are we comparing these two things and make a decision whether to continue execution over here or continue execution over here? So all of those will become, I hope, crystal clear in this class. Also, how subroutines call, okay? How can we call a subroutine and know where to get back to? Some of you may be exposed to the concept of a stack because your CISP310 professor talks about it. Some people may have no exposure whatsoever to the concept of a stack. But in this class, we also take a microscopic view of calling and returning, as well as how do we pass parameters. What about the return value of a subroutine? How do we do structures, arrays? How do we use pointers and dereference? And how do we get the address of a variable? What is a local variable? What is a global variable? We'll get to all of those concepts that you already know in your C++ class, except this time, I'm going to give you the X-ray vision into your C++ code so that you know exactly how memory is organized when you execute those programs. Some of you will continue to write programs in C++ or C in the future. Knowing how memory is organized can really help you debug programs. Because you can remind me later, but I can write code where it is buggy, where the symptom cannot be explained, even if you know your C++, upside and down and whatnot. Because the symptom has to do with the corruption of the stack. So if you don't know what is happening on the stack or how the stack is used, then the symptom becomes unexplainable. Main calls F, when F returns, it goes to some other subroutine other than main. Or you can call a subroutine, when the subroutine returns, all the variables are quote unquote shifted. Variable X becomes variable Y becomes variable Z, they're all shifted down a little bit. What just happened? So hopefully this class will help you understand all of those things in case you have to program in C or C++ in the future. I think most of you will, because most 4-year universities still teach C++. So, all right. So you guys have all the things that you need to get started with the lab. This one is going to be a little bit lengthy, so I will just kind of get started as soon as you get to the lab.
I just take a picture of the writing and what's it?
Well, it's all getting recorded. Do you want to take a picture of the circuit itself?
Yeah.
You mean like this one?
Yeah.
Okay.